This is the part 2 of steel columns calculations. Past class, we look at the referring Euler buckling, and we see some of the formulas. And we understood that the failure in a column depends of the proportions. When we have columns that are very long, they will fail by buckling, as we can look here. In the left side, in the right side, when we have columns that are short, usually we will have a crushing, and intermediate columns can fail by crush or buckling. Well, I explained information related with steel columns, the end conditions, the slenderness, and we did one first example where we need to calculate a specific K. Thereafter, determine the column slenderness, thereafter the critical stress, and finally to determine the safe load that a column have. All this was possible using some tables. However, columns also have a safe axial load that depends of the axis. When we have an I-beam, for example, we have an axis where it will be more difficult that the beam fell by bending. That will be something similar to move in that sense or move in this sense. Well, it's obvious that this column in this axis is more easy to move than in the axis that we have there. Because we have an I-beam, there is more steel in the top and in the bottom. Therefore, it will be difficult that this column bend in this sense and became something like this. It will be easier to bend in this side and became something like that. Well, it's important to understand which of the axes is the one that is more negative in order to use that axis to do the calculations, because if this column is able to resist a load in all these axes, it may not resist a load. It will resist a load in this other axis because it's stronger. Well, usually we need to do a design that help us to, let me go back a second. Let me clean everything. That will allow us to use a trial and error approach. Well, we will have a critical stress that cannot be determined until we have a shape, and having the shape, then we can try if the critical stress is adequate or not. Well, there are some loads tables that will help to do some of the calculations. But when we have built up sections, we need to use this approach because we cannot apply safe load tables to the design. Well, when we design different type of columns, usually we're speaking about I-beams or A-shape. A-shape because, as you know, we have something that is almost a square for the column, and usually we have something that is like this for a beam, like that, with the loads never apply in this sense, but applies in this sense. And for the other one, obviously the loads are applied in the top. We have two types of steel, and we have a different type of steel grade. Well, we have tables that will help us to understand that kind of loads, and we already used them during past section. We can look here, one of the tables. In the table, we will have the type of steel, and in this case, all the table is related to 36 KSI. I mean, this steel is able to support the 36,000 kips per square inch. We have the different types of columns. Well, in this case, we have a W. A W is this one with a denomination that is W, the type of beam that is similar to an I-beam, like Mohr square. 14, that is how high this element is. And we speak about the height because this element is also used for beams. And 211, that is the weight of 1 foot of this particular material. Well, let's tell that here we have columns that are all have a height of 14, but they have different weight. The weight is very important because, as you know, we buy the steel according to the weight, the number of tons that you are buying. And well, when we have a steel that is, for example, 82, mean the weight of this particular column is 82 pounds, but you have another one that is, for example, 176, it's obvious that the element that is 176 is more than twice the price, because always the price came by weight. Well, it will be good that we use, when we have the option, we use the steel that has less weight. Well, if all these columns are able to support the same, the load that we want to support, it will not be the same load because obviously the thickest, the stronger is the column. But if all of them are able to support our load, obviously we will choose the one that have less weight, that is the 14 by 53. After we have the ratio, and this is a ratio between the relationship between both axes of the column, and it's a number. And after we have the length of the material. And the length of the material, 0 means from 0 to 6. This is a column of 6. This is a column of 8. This is a column of 14. Well, that is how long the column is this distance that we will have from the top to the bottom. Well, for every length, for example, this is a column that is 12 feet long, we will have a specific KL of each one. That is the safe load that the column can support, that in this case is 1,142 kips. Let me go back. We have the same, but with a steel of 50. Exactly same table. Usually for the test, we use 36. 50 KSI is the steel that we use for very tall building and skyscrapers. The 36 is the using normal construction. Well, we will look at example number 2. And what we will do here is different what we did before. Before we have a specific conditions and an end condition and a specific description, and we need to look what is the load that this element is supporting. In this case, we already know what load we will have. Well, in this particular situation, we have an axial load of 100 kips that is dead, and 150 that is live. Okay, and we already know what is dead loads and live loads. Well, the total load is 250. The column have a length umbraced of 24. Maybe the column is much longer. It's a column of a very big building, but the section that we're calculating, it need to be an umbraced section of 24 feet. The end conditions are pine at the top and at the bottom. Always for these calculations, we have pine at the top and bottom, always. Therefore, K will be always 1. Therefore, we will never use K. We will not use K in the formulas, okay? Let me go back. Well, this is very simple exercise. What we will do, we just need to calculate the total load, but the total load is not 100 plus 150. Why? Because there are security factors. Well, we want to make sure that the column is supporting the weights, and if the load that we expect that will support is 100 kips, we need to multiply 100 kips by 1.2, make 100 kips 20% bigger. And if the dead load is 150 kips, we need to make sure that is 60% bigger, where we will multiply by 1.6. That is always like this. Well, dead load by 1.2, multiply 100 kips, plus the live load of 100 kips, 50 kips multiplied by 1.6, both together are the load that this element this column is supposed to support, and it's 360 kips. Okay, again, this is a security factor. It's just in case. We don't want to calculate a beam exactly with the same, a column exactly with the same loads that is supporting. We imagine that it's supporting more. Why? Because it's part of a building, and maybe in some moment you will have more people of the people that are supposed to be there. Maybe you will have some furniture that is heavy, that is bigger than the one that is supposed to be there. And maybe there is a small mistakes with the dead load, or there are elements that are fixed that are installed later on. Therefore, we make also the dead load only 20% bigger, but the life 60% bigger. When we have this number, 360, is very easy. We just need to look at our column, okay? We don't need to use the radio. We don't need to use K. We don't need anything. We just need to move our, let me go back here, our vertical line and choose the one that in our case is 24 feet, and after choose any number that is number of 361 as a possible candidate. 360, sorry. Well, we have 361, we have 444, we have 442, and obviously we can use many others. We can use also 548. We cannot use 128 because it's smaller than 360, but we could use 1,399, etc. Well, we don't want to go to a number that is too big, because if the number is too big, probably the weight of the material will be bigger. For example, here between all the 14s, all these start from here to here, okay? We have two that cannot be chosen, 53 and 68. Well, we choose the next one, that is 14 by 82. We will not choose the one in the top because it's heavier. Well, this one seems to work very well. Between the 10s, we can choose the one that support more than 360, and obviously is this one, 12 by 79. Between the 10s, we have, this one is impossible, it's less, this is the one. Between the 8s, we don't have any. There is no column with a height of 8 that can support that way. Well, we have already our candidates, and we want which one we will choose. Obviously, the one that have less weight, 12 by 79. And you have all the explanation just in the next slide. The possible choice, and if no other parameters are required, the choice on which selection should be the one that is cheaper, 12 by 79. If for any reason we cannot have a beam that has this high, 12 by 79, because it's too high, we will not be able to, sorry, we have a column, it's not big. We have a column, and this column is taking too much space, is not working well, then we can go to one that is a little bit cheaper, a little bit more expensive, but it's a little bit smaller, that is W10 by 88. But in our case, in the test, we will also choose the one that is less heavy, that is the cheapest one. And that is all for this type of problems. Thereafter, Let me go to the slideshow. Well, I will keep it like this. I think that is better. Thereafter, we need to understand that the use of safe loads have to do with the radius of gyration that the element have. We also need to understand that K is always 1 because we have an end condition that is 1. And in this particular case that we have with this kind of beam, the y-axis must be the most slender. Well, always everything related with KL divided by R will be the biggest one. Therefore, always we have end conditions that are the same in both axes. The umbrace length is equal. The umbrace length in the y-axis is bigger than in the x-axis because we are doing with this kind of beams. Well, we need to have these conditions in order to resolve this type of beams. And we will look at the last example, that is example number 3. In this, we will also select an A36 steel column section for an axial load of 100 kips depth, 150 live, and the umbrace length is 24 feet about the x-axis, and the umbrace length is 8 feet about the y-axis. Well, 24 is bigger, we will choose 24. We understand that that is our worst case. And then conditions are fine at the top and at the bottom. Well, again, we don't need to use a K factor because it will be 1. The axial load is the same that we had before, is 360 kips. We have the same load. Well, we need to select which kind of steel column section we will have. First, we make sure that we have a radio umbrace length about the two axes that is adequate, because the difference between them cannot be that huge. This is something that is very relative. You don't need to do these calculations for the test. I will always make sure that the radio is adequate. And what we will do here is to apply the same formula, KL divided by R. Okay? I didn't write the R here. I forgot in the element, but I will write later on. The R is is 1.75, and we can find that number many times in tables. And well, we just multiply K, that is already 1. We don't need to use it. L is the umbrace length that is bigger, that is 24. We divide by the R, by the radius, that is 175. And that gives us a proportion of length of 13.7. And 13.7 is 14. Okay, well, we will do the approximation. If you have 13.2, you will use 13. If you have 13.5, you will use 14. Well, we go to 14, and this is the particular length of the column that we calculate. And we know that this column is supposed to resist 360 because it was like one before. Well, we look among the columns that are 14 high, which one support a more than 360. And well, it seems that 14 by 53 doesn't work, and the next one is 14 by 68. Obviously, we can use also 14 by 82, 14 by 120, but those are heavy sections. The weight of 120 is almost twice than the one of 479. Well, we'll use 14 by 68. And we look the same with one of 12, and we choose 12 by 53 because the 45 is too small, doesn't resist. And we look if we have 1 in 10, and we have 10 by 54, that resists 386, that is more than 360. And finally, we have 8 by 58, that is able to resist 374. Which one we will use? Well, some of you will tell, I will choose this one because it's smaller. Yes, it's smaller in dimension, it's 8, but the weight is 58. This is thicker. This one have less weight. 10 by 54 have less weight. 12 by 53 have even less weight. 14 by 68 is too heavy. Well, W 12 by 53 is the one that we need to use because it's the one that have less weight. And remember, the second number is the weight of 1 foot of that material. And that's it. There are other calculations that we will not do in this class, but engineers use different tables for other type of elements. Remember that always we need to have this safe table and choose the adequate slenderness radio. I will give you the slenderness radio. You don't need to calculate. You already have Rx divided by Ry. There are also calculations for steel pipes. The steel pipes are divided in different types. In the case of them is the type of steel, like you have a weight that is standard, extra strong, and double extra strong. Well, that means that the pipe is thicker and is stronger. And there are tables that I just took out from the presentation because some students got confused and after used the wrong tables to do so. Also, for other elements like tubing columns, you can even do calculations for things like trusses, etc., etc. When we speak about the bending of the column, we need to understand that obviously depends very much of what the column is supporting. Like this column have a cantilever, this one have a beam. Well, the beam is longer and will produce more bending. And also when we have a weight in the top of the beam, we can also have weights in the sides, and that can produce bending because we can have strong winds that are pushing the columns in one side. Well, there is always like some calculations for windings that we will not be calculating, but are part of this kind of elements. And after, it's necessary also to calculate the base of the column because the foundation will be supporting it. Well, normally there is a plate that is larger than the column that will accommodate anchor, bolts, and welding. And that's something that we will be looking later on. Bases can be calculated according with these formulas. We will not doing that, it's only for your information. And well, we can look here the type of thickness that the base of the column can have. Well, when we have a column that is made out of steel, usually there is a base plate that is normally welded to the material, and that base will help us to locate and attach the material in the place that is supposed to be. And well, we have here again the tables that we will be using for this class. And this concludes this presentation.